On February 11, 2026, China launched the Long March 10 rocket from Jiuquan carrying a full-scale crew capsule designed for lunar missions. This wasn't a test article, this wasn't a boilerplate mock-up. This was flight-rated hardware, executing a dual mission profile that no other nation has attempted in a single flight. The rocket performed a high-altitude launch abort system test, while simultaneously demonstrating controlled propulsive landing of its first stage at 105 kilometers altitude. NASA's Space Launch System costs $4 billion per launch, according to NASA's own Inspector General. China is targeting a crewed lunar landing by 2030, potentially accelerated to 2029. But this isn't just a story about a rocket. The real story is what happens when flight-tested hardware validates an entire lunar architecture while the world is still debating timelines. For 60 years, the rule was simple. Building a heavy-lift rocket capable of lunar missions required decades of development, hundreds of billions in funding, and institutional knowledge that only legacy space agencies possessed. The Saturn V took 8 years and consumed a significant fraction of America's GDP. The Space Launch System took 17 years and cost over $23 billion before its first flight. The engineering challenge wasn't just thrust or payload capacity, it was systems integration across thousands of contractors, political continuity across multiple administrations, and the brutal physics of scaling rocket engines to moon-class performance levels. Every Western aerospace analyst operated from the same assumption. China would follow the same timeline. They would build incrementally. They would test cautiously. They would arrive at the moon sometime in the late 2030s, maybe early 2040s if everything went perfectly. The Long March 10 changes that calculation completely. 70 tons to low Earth orbit, 27 tons to translunar injection trajectories, payload capacity directly comparable to NASA's Space Launch System, but with cleaner architectural design focused on reusability from day one. This isn't a prototype sitting in a hangar awaiting funding approval. This is flight-tested hardware that just validated its launch abort system and demonstrated controlled propulsive landing in a single integrated mission. The China Manned Space Agency completed development and testing faster than any comparable Western heavy-lift program. And the triple-core configuration with comprehensive reusability architecture fundamentally alters the economics of sustained lunar operations. Once initial vehicle development is complete, marginal cost per mission drops dramatically. That makes the difference between flags and footprint symbolism and actual infrastructure. To understand how this all happened, you have to go back to where it started. But here's the part that makes aerospace engineers stop and recalculate their timelines. The Mengzhou crew capsule and Lanyue lunar lander aren't concept drawings or wind tunnel models. They're operational vehicles that have already completed critical flight testing. The February 2026 launch carried the Mengzhou capsule through a high-dynamic abort profile specifically designed to validate translunar mission parameters. This was the first time China publicly demonstrated full-scale integration of lunar-class hardware in an actual flight environment under maximum aerodynamic stress. The Mengzhou capsule itself represents a clean sheet design optimized for deep space operations. Unlike earlier Chinese spacecraft derived from Soyuz heritage, this vehicle was engineered from the beginning for translunar trajectories, lunar orbit operations, and high-speed atmospheric re-entry at escape velocities. The thermal protection system, guidance computers, and life support architecture all reflect mission requirements that only apply beyond low Earth orbit. China didn't retrofit existing hardware. They built purpose-designed lunar vehicles. The Lanyue lander completed even more comprehensive testing in late 2025. The vehicle's landing legs, descent engines, and ascent engines all performed exactly as designed during ground tests that simulated lunar gravity and vacuum conditions. The descent engine throttling range, propellant management systems, and automated landing radar were validated in integrated test campaigns that replicated actual lunar approach profiles. This wasn't component-level testing. This was full vehicle validation of every critical system required to land humans on the lunar surface and return them to orbit. The timeline now projects an uncrewed test flight of the complete lunar mission stack in 2027 or 2028. That mission will demonstrate the full sequence. Launch on Long March 10. Translunar injection. Lunar orbit insertion. Rendezvous and docking between the Mengzhou capsule and Lanyue lander in lunar orbit. Separation and descent to the surface. Ascent back to orbit. Docking again with the return capsule. Trans-Earth injection and high-speed re-entry. Every phase of the crewed mission profile will be validated with actual flight hardware before any astronauts board the vehicle. This is the same methodical test philosophy that characterized China's space station program. Prove every system works in the real environment before committing crew. And that same pattern is exactly what makes the 2030 crewed landing date credible instead of aspirational. Now here's the part that makes the timeline work. China did not decide in 2023 to suddenly put astronauts on the moon. The foundation was laid 2 decades earlier, mission by mission, each one validating a specific piece of the puzzle. Every success, reduced risk for the next step. The Chang'e program began in 2007 with orbital reconnaissance. Chang'e 1 mapped the lunar surface. Chang'e 2 refined those maps and tested deep space communications. These were not glamorous missions, but they established ground station protocols and navigation precision. By the time Chang'e 3 landed in 2013, Chinese engineers had already logged thousands of hours operating spacecraft in lunar orbit. Then came the methodical escalation. Chang'e 3 proved soft landing technology in Mare Imbrium. Chang'e 4 landed on the far side in January 2019, a first for any nation, supported by Kuiqiao relay satellite positioned at the Earth-Moon Lagrange point. That relay architecture became critical. You cannot communicate directly with the far side. The signal has to bounce through a satellite parked in gravitational balance 64,000 kilometers beyond the moon. China built it, deployed it, and operated it flawlessly for years. Chang'e 5 returned samples from the near side, in December 2020. 1,731 grams of lunar regolith delivered to Earth after a 23-day mission. Then Chang'e 6 did it again in June 2024, but this time from the far side. First nation to accomplish that specific feat. Each mission systematically validated a different operational requirement. Orbital rendezvous, ascent from the lunar surface, sample container transfer in lunar orbit, re-entry at Earth return velocities exceeding 11 kilometers per second. In April 2026, the Chang'e 7 spacecraft was transported to Wenchang Satellite Launch Center. Launch window opens in August 2026. The mission will deploy a relay orbiter, a lander, a rover, and a small flying probe to explore permanently shadowed craters at the lunar South Pole. That is 4 separate vehicles operating in coordination, scouting the exact region where the International Lunar Research Station will eventually be constructed. By the time astronauts arrive, Chinese Mission Control will have managed complex, multi-vehicle lunar operations for years. The Long March 5 family, as of April 2026, had flown 17 missions with 16 successes. Cumulative success rate of 94.1%. Not perfect, but reliable enough to bet crew on. And each Chang'e mission flew on a Long March 3 or Long March 5, steadily building launch cadence and operational confidence. This is not a crash program. This is incremental capability building across 20 years. But here's what nobody is talking about. But here's the trick. China is not planning a few landings and then going home. The target is a permanent research presence at the lunar South Pole by approximately 2030, not flags and footprints. Infrastructure. The International Lunar Research Station, or ILRS, represents a fundamentally different model than Apollo. Apollo was about demonstration. Get there, prove it can be done, leave. The ILRS is designed for continuous occupation and resource extraction. The location was not chosen for symbolism. It was chosen for water ice deposits in permanently shadowed craters. Water is not just life support. Water is hydrogen and oxygen. Hydrogen and oxygen is rocket fuel. If you can extract and process water on the moon, you do not have to carry all your propellant from Earth. The energy cost to launch from the lunar surface is roughly 1/20th that of launching from Earth. Lower gravity, no atmosphere. This matters because the moon becomes a staging point. If your goal is Mars, or asteroid mining, or deep space operations beyond the Earth-Moon system, launching from the moon instead of Earth changes the entire economic equation. China has stated this explicitly in planning documents. The ILRS is not the destination, it is the gateway. Construction is planned in phases. Initial robotic landers deliver habitat modules, power systems, and resource extraction equipment starting around 2028. First crewed missions overlap with robotic build-out, gradually extending surface stay durations as infrastructure comes online. By the mid-2030s, according to Chinese Space Agency projections, the station supports rotating crews conducting materials science, astronomy, and in-situ resource utilization experiments. Permanently shadowed craters near the South Pole also offer thermal stability. Temperatures in sunlight swing from 127 degrees Celsius to minus 173 degrees Celsius. Inside the permanently shadowed regions, it stays cold, but constant. Easier to engineer for. China is also positioning the ILRS as an alternative to the Artemis Accords framework. The Accords, led by the United States, establish principles for lunar exploration, including resource extraction rights and safety zones. China and Russia declined to sign. Instead, they are building a parallel governance structure. The ILRS partnership currently includes Russia, Venezuela, Pakistan, South Africa, and the United Arab Emirates, with more nations expressing interest. This is not just about science. This is about who writes the rules for the next phase of space activity. The moon has no territorial sovereignty under the Outer Space Treaty of 1967. But if you build the infrastructure, you set the operational norms. That is not just exploration, that is strategic positioning. But if you think lunar infrastructure is the only race happening, you have not seen the American side. By 2025, the cost difference had become impossible to ignore. NASA's Space Launch System, the rocket designed to return Americans to the moon, costs approximately $4 billion per launch, $4 billion. According to the NASA Office of Inspector General, that figure represents extraordinary cost escalation driven by legacy contractor structures and program management challenges. The Artemis program, America's lunar return initiative, has faced multiple delays and ballooning budgets. Artemis 1 flew uncrewed in November 2022. Artemis 2, a crewed lunar flyby, has been delayed to 2026. Artemis 3, the actual landing, is now projected no earlier than 2027, and many analysts consider that optimistic. Complex contractor coordination across Boeing, Lockheed Martin, Northrop Grumman, and SpaceX has created integration challenges that slow every milestone. Meanwhile, China in 2025 conducted 92 space launch missions. That is a 35% increase compared with 2024. Of those, the vast majority were successful. The Chinese space program operates under a single integrated agency, the China National Space Administration, with direct coordination between launcher development, spacecraft design, and mission planning. There is no bidding war between competing contractors. There is no political fight over which state gets which factory. Development happens in parallel under unified program management. The American advantage in aerospace engineering, unquestioned since the 1960s, is now being challenged not by superior technology, but by systematic infrastructure development and cost discipline. SpaceX has disrupted part of this equation with Falcon 9 and Starship, bringing launch costs down dramatically through reusability. But SpaceX is one company. China's approach involves an entire national industrial base retooled for space logistics. State-owned enterprises like the China Academy of Launch Vehicle Technology operate with long-term funding certainty and centralized decision-making. The Long March 10, at roughly 1/7 the per-launch cost of SLS, reflects that structural difference. It is not that Chinese engineers are better. It is that the system is optimized differently. Lower labor costs, vertical integration, and state-directed investment all contribute. And here is the staggering part. NASA's current timeline has Artemis 3 landing near the lunar South Pole no earlier than 2027. China's timeline has Mengzhou and Lanyue doing the same thing in 2030, 3 years later, but with a fully operational heavy-lift rocket that costs a fraction as much and is designed for reuse from the start. This is not American failure. This is Chinese acceleration. Here is where it gets staggering. But here is the trick. In February 2026, China conducted a controlled propulsive landing test of the Long March 10 first stage at an altitude of 105 kilometers. The booster fired its engines, slowed itself down, and descended under power exactly as planned. This was not an afterthought. This was not a retrofit. This was designed in from day one. SpaceX proved the economics with Falcon 9. Land your first stage, refurbish it, fly it again. The marginal cost per launch drops by more than half. You can fly missions that would never pencil out with an expendable rocket. You can sustain a cadence that would bankrupt any program burning hardware on every flight. China watched. China learned. And then China applied that same principle to a vehicle twice as powerful. The Long March 10 is not just reusable in theory. It is being built around reusability as the baseline architecture. The propulsion, the avionics, the structural margins. Everything sized to survive re-entry, reignition, and touchdown. The landing legs are not bolted on as an experiment. They are load-bearing members of the design. This is what enables high-cadence lunar operations. You cannot sustain multiple crewed missions per year if every rocket costs $500 million and gets thrown away. You cannot build an international lunar research station if the transportation system eats your entire budget. Reusability is not a luxury. It is the economic foundation of everything that comes next. And China is not testing this on small demonstrators. They are validating it on the actual lunar rocket. Full scale, full thrust, full mission profile. Expected later in 2026. The first full-duration static fire of the triple-core configuration. All engines, all stages, all systems firing together for the first time. This is not incremental development. This is systematic validation at operational scale. But if you think the hardware is moving fast, you have not seen the timeline. When you step back and look at everything China has built over the last 3 years, the pattern becomes impossible to ignore. The rocket flew, the capsule flew, the lander flew. The reusability test succeeded. The infrastructure is operational. Every critical system has been validated in the actual flight environment, not in PowerPoint, and the timeline just accelerated. Official target: crewed lunar landing approximately 2030. But following the successful February 2026 integrated test, internal projections now suggest potential acceleration to 2029 or even early 2030. The projected 2027 debut orbital flight of the full-scale lunar rocket represents a compression of the schedule the compression of the schedule compared to previous timelines. This is not hope. This is confidence. Confidence that comes from watching your hardware perform exactly as designed under real conditions. In July 2023, China announced its intention to land taikonauts on the moon before the end of the current decade. They are now tracking ahead of that commitment. Schedule compression like this does not happen by accident. It happens when every subsystem validates on time, when your rocket works, when your capsule works, when your lander works, when the pieces fit together the first time you try. And here's the question nobody in Washington wants to ask out loud. What happens when the world watches Chinese astronauts walk on the lunar surface while America is still building its rocket? If you made it this far, hit like and subscribe so you never miss the next one. Because we have more jaw-dropping engineering and infrastructure stories coming that you are absolutely not going to want to miss. Stories about projects that are rewriting what is possible when planning, execution, and political will align. Here is your question. If you could build one infrastructure project anywhere in the world that would change the trajectory of human spaceflight the way Wenchang has,